working through the Chapter 7 review in pre-calculus. And feel free to just fast forward to whatever problem you need. I'm going to work through all of them in order so you can just find whatever problem you need. Number 1 says simplify cosine x cosecant x over tangent x. So in this case, since it's kind of a mixture of trig ratios, we're going to start by rewriting everything in terms of sine and cosine. So we'll leave it as cosine x. We'll turn cosecant into 1 over sine x. And then in the denominator, we'll turn tangent into sine x over cosine x. All right, so now we can combine the numerator into a single fraction. Cosine x times 1 is cosine x over sine x, and then that is also over sine x times cosine x. Now we can do keep switch flip, so you can only do keep switch flip if there's a single fraction in the numerator and a single fraction in the denominator. So keep the top as cosine x over sine x, and then flip the bottom and make it cosine x over sine x. Now if we multiply straight across, we have cosine squared x in the numerator and sine squared x in the denominator, and cosine over sine is cotangent, so we can just rewrite this as cotangent squared of x. So once you get it down to a single trig expression, that's usually where you want to end these types of problems. Let's move on to number 2. So in this one we have to verify, so we know what we're trying to get the left-hand side to equal. And you never mess with the right side when you're doing, when you're verifying these. So first, if I have cosecant and sine, I'm probably going to want to turn this cosecant into 1 over sine x. And then what I'm going to do right away is actually get a common denominator. So I'm going to put this sine x over 1, and I'm going to multiply the top and bottom by sine x. So this is going to turn into sine squared x over sine x, which is the same thing as sine x, but now I can combine these into a single fraction. So my common denominator is sine x, so in the numerator I can just subtract 1 minus sine squared x all over sine x. And you probably are recognizing that this is a Pythagorean identity. If you notice your Pythagorean identities, cosine squared x plus sine squared x equals 1, so that can actually be replaced with cosine squared x. And if you want an explanation on to why that is, you just send me an email and I will explain it to you. All right, but we still have that as over sine x. And now what I'm going to do is actually separate this so that we can do one last step here. So instead of putting cosine squared x, let's say this is cosine times cosine. That's the same as cosine squared x, right? And then we're going to split this into 2 separate fractions. So on the bottom, I'm going to think of this as 1 times sine x. So this is cosine x over 1 times cosine x over sine x. Well, now you can probably see where we're going to end up. Cosine x over 1 is just cosine x, and then cosine x over sine x is cotangent x. So we ended up with the same thing on the right-hand side as we have on the left-hand side, and that is verified. Okay, let's look at another one of those and a number 3 here. So right off the bat, we have a Pythagorean identity here. Tangent squared x plus 1 can be replaced with secant squared x. So we're going to start with that. So cosine x times secant squared x. And again, we're only going to deal with the left-hand side of this equation. So don't do anything with the secant x on the right-hand side. All right, now let's rewrite that in terms of cosine. So this is cosine x times secant is 1 over cosine. So this will be 1 over cosine squared. And what's going to happen here is this cosine squared is going to cancel out one of the cosines here, and we'll just end up with 1 over cosine x. Well, 1 over cosine is secant. So we ended up with the same thing that we have on the right-hand side, and that means this is verified. All right, so let's move on to number 4. This one is still a verifying one, and this one's going to be a little bit more involved here, but we are going to start by turning everything into terms of sine and cosine. So let's turn cosecant into 1 over sine x minus cosine x over sine x all over, and then the secant we will turn into 1 over cosine x. And what I'm going to do right away is I'm going to turn this minus 1 into minus cosine x over cosine x, because I know I'm probably going to have to combine these into a single fraction, and in order to do that I will need a common denominator. So I'm just doing that right away. So now that's what I'm going to do. I'm going to combine these numerators into a single fraction up here and combine these denominators into a single fraction down here. All right, so in the numerator I have 1 minus cosine x over my common denominator, which is sine x, all over 1 minus cosine x over my denominator, which is cosine x. And now that we have those into a single fraction, we can do keep switch flip. And you're probably running out of room down here, so maybe let's just continue this problem over here. Again, we're trying to get this to be equal to cotangent x. And from this step, we're going to do keep switch flip. So I'm going to say 1 minus cosine x over sine x times the reciprocal of my denominator, which would be cosine x over 1 minus cosine x. And now you can probably see where we're going from here. This 1 minus cosine x cancels this 1 minus cosine x. So in the numerator, we just have cosine, and in the denominator, we just have sine. So cosine x over sine x, hopefully you recognize that is actually cotangent x, which is what we have on the right-hand side, and that means we have verified this identity. Okay, so we're going to switch gears a little bit here in number 5, and it says to find the exact value of sine 42 degrees cosine 12 degrees minus cosine 42 degrees sine 12 degrees. So hopefully you have your formula sheet filled out so you don't have to flip through your notes, but this is actually a difference formula, and you don't have to write the formula down, but the formula that they're using here is the difference formula that says sine of x minus y is equal to sine of x times cosine of y minus cosine of x times sine of y. So what I do in this type of problem is I look at my identities and I try to find one that looks similar to what I'm given here. So hopefully you can see that this is very similar. The only thing they're doing is replacing x with 42 degrees and y with 12 degrees. So we're going to use this side of the equation and plug in 42 for x and 12 for y. And that's just going to become 42 degrees minus 12 degrees, which hopefully you recognize is just the sine of 30 degrees, which is just a point on our unit circle. So I'm asking myself, at 30 degrees, what is the y value of that terminal point? Well, it's 1/2. So that's our answer. So I don't want you to just plug this in a calculator and figure that out. I should be seeing you using some sort of identity to find that. If it says exact value, chances are you're using one of those identities on your formula sheet. Okay. So number 6, kind of the same idea. Now they say I'm going to use a sum formula. So look at that part of your formula sheet. And you're just asking yourself, okay, on my unit circle, are there two nice degree measures that I can add together to get 105 degrees? Well, hopefully you can see that sine of 60 degrees plus 45 degrees is the same as sine of 105 degrees. And then we can use the sum formula. And again, you don't have to write this formula down, but this is where I'm getting this. It's sine of x plus y is equal to sine x cosine y plus cosine x sine y. So we're just going to replace the x's with 60 degrees and the y's with 45 degrees. And here's what that's going to turn into then. Sine of 60 degrees times the cosine of 45 degrees plus the cosine of 60 degrees times the sine of 45 degrees. Now the reason we did that is because these right here are all values that are on our unit circle. So hopefully you recognize that the sine of 60 degrees is on our unit circle, and that value is just root 3 over 2. The cosine of 45 degrees is root 2 over 2, plus the cosine of 60 degrees is a half, and the sine of 45 is also root 2 over 2. So now we can just multiply. Root 3 times root 2 is root 6. 2 times 2 is 4. Plus 1 times root 2 is root 2. 2 times 2 is 4. And we have a common denominator, so our answer is just going to be root 6 plus root 2 all over 4. All right, so again, you're not just plugging this into a calculator and spitting out the decimal. I want to see the exact value, so you should be using one of those identities. Okay, let's move on to number 7. And this one says, use the given drawings to find sine of a minus b and simplify your answer. So in this triangle with angle A, hopefully you recognize that this is a Pythagorean triple, 5, 12, 13. And if you weren't sure about that, you could always just do your 5 squared plus 12 squared equals c squared and solve for c. I guarantee if you do that, you'll get 13. So I'm not going to do that, but you could if you weren't sure. And this other triangle is a 3, 4, 5. So with both of these, what I'm going to do is just jot down below what the cosine of angle A is. So that's our adjacent over our hypotenuse. So the cosine of A is going to be 12 over 13. And then the sine of angle A is going to be our opposite over hypotenuse. All right, same with this triangle with angle B. So cosine of B is 3 over 5. And then the sine of B is 4 over 5. All right, so why do we need to do that? Well, when we're using the difference formula for sine of x minus y, or in this case, sine of a minus b, it's going to turn into this. So sine of a minus b, if we expand that out, is sine of a times the cosine of b minus the cosine of a times the sine of b. All right, well, we know what the sine of a equals. It's right here. So we're just going to replace the sine of a with 5/13. And we're going to do that with all of these fractions. The cosine of b is 3/5 minus the cosine of a, which is 12/13, times the sine of b, which is 4/5. So that's what these triangles helped us do. They helped us figure out what the values of each of those trig expressions are so that we can just replace those fractions with the trig ratios. All right, so now, oops, I meant to erase that. So now we can just multiply. We get 15 over 65 minus 48 over 65. And we have a common denominator, so we can just subtract 15 minus 48 is negative 33 over 65, and that would be our exact answer. All right. Okay, let's move on to number 8. And 8 and 9 both use this information that the cosine of x is 1/3 and x is a 4th quadrant angle. So let's draw what that means. So here's just a little coordinate plane. And in the 4th quadrant, we have our angle x. And that x has a cosine value of 1/3. So we know our adjacent is 1 and our hypotenuse is 3 because cosine is adjacent over hypotenuse. So now we can use the Pythagorean theorem to find the opposite. So I'm going to do 1 squared plus b squared equals 3 squared. So if I got b by itself, I'd go ahead and subtract 1 from both sides. So minus 1 squared minus 1 squared. And we get b squared equals 9. Just kidding. B squared equals 8. And if we take the square root of that, b is going to be, let's split that into root 4 times root 2. So b is 2 root 2. All right. So why we had to find that is because we're going to need to know the sine value of this triangle. So off to the side here, I'm just going to write, based on what I found here, the sine of my angle x is going to be my opposite over my hypotenuse. So I'm going to need to use that when I figure out number 8 and 9 here. So you have a double angle formula, which says that the sine of 2x is equal to 2 times the sine x times cosine x. Well, we just figured out that sine x equals this. So I'm going to say this is 2 times 2 root 2 over 3. And then we know what cosine x equals. That was given. That was just 1/3. All right, so now we can just put this 2 over 1, multiply all the numerators together, and we get 4 root 2 over 9. And I'm noticing that I forgot something very important here. Since we're in the 4th quadrant, this should actually be a negative 2 root 2, so my sine value should actually be negative. So let me just add that on here. So sine of 2x should be a negative 4 root 2 over 9. All right, so don't forget those negatives and positives. Those are important when you're figuring these out. All right, now number 9, when you use the double angle formula for cosine, there's 3 choices. To be honest with you, I always use the cosine squared x minus sine squared x version because then you don't have to find a common denominator. So I'm doing that, but if you use either of the other 2, you will get the same answer. So for cosine squared x, we can plug in 1/3 and then square it. For sine, we can plug in negative 2 root 2 over 3 and then square it. So if we square 1/3, we get 1/9. If we square negative 2 root 2, that square actually applies to both of those, so it ends up being 4 times 2, which is 8. And then in the denominator, 3 squared is 9. So that's why I like to use this version, because now notice I have a common denominator and I can just subtract. 1/9 minus 8/9 is negative 7/9. And then I am done. All right. Let's move on to number 10. Number 10 says find the exact value of cosine of 22.5 degrees using the half angle formula. So hopefully you recognize that 22.5 degrees is half of 45 degrees. So we're going to rewrite this as the cosine of 45 degrees over 2. Because then we can use the half angle formula for cosine, which says plus or minus the square root of 1 plus cosine of x. Well, in this case, our x is just that 45 degrees. So I'm going to plug that in right away. And that is all over 2. Okay, and again it says find the exact value, so we're not just plugging into a calculator, we're using our identities to simplify this down. So you have to figure out, first of all, are you going to use the positive or negative? Well, 22.5 degrees is in quadrant 1, so that means we are going to choose the positive because we know cosine is positive in quadrant 1. All right, so now we just start simplifying. We have positive square root of 1 plus the cosine of 45, that's on our unit circle, that's just root 2 over 2, all over 2. So what I'm going to do is split this up. 1 divided by 2 is a half, plus root 2 divided by 2 is actually just root 2 over 4. And that's still all under the positive square root. So now we probably should get a common denominator. So I'm just going to do this. I'm going to change this to 2/4 right away. And then just say that this is 2 plus root 2 all over 4. And now I can go ahead and take the square root of that. The square root of the numerator is just root 2 plus root 2. The square root of the denominator is the square root of 4, which is just 2. And then again, that's positive. You don't really need to put the plus symbol there, but I just like to emphasize it. All right, so that gives us our exact value of number 10. Now, I know if you look at the key that's posted in Canvas, if you have that, it's going to look like this, positive 1/2, and then times the square root of 2 plus root 2. Same thing. So it doesn't matter to me how you write it. They are equal. Okay, let's look at number 10. So in this case, it says find the exact value of sine of x over 2, given that sine of x is 5/13 and x is in quadrant 2. So first, let's just draw a little picture of this. So I'm going to draw a second quadrant angle and call it x. And if sine of x is 5/13, that means my opposite is 5, and my hypotenuse is 13. And then hopefully you notice that this is a 5, 12, 13. But if I'm in quadrant 2, that's going to have to be a negative 12. All right. Now, if I'm trying to find sine of x over 2, I'm going to be using a half angle formula, which, if you look on your formula sheet, says that you have positive or negative square root of 1 minus cosine x all over 2. So you, again, have to figure out if you're going to use the positive or negative. So our x is in quadrant 2, but if we divide it by 2, it's going to actually end up being somewhere in quadrant 1. So we are going to choose the positive value, okay? And because we know sine is positive in quadrant 1, it's also positive in quadrant 2, so in this case you'd be safe either way. But you have to base it off of after you divide your angle by 2. All right, so now we can just start plugging stuff in. So based on our picture here, we know that the cosine is our adjacent over our hypotenuse. So we're just going to replace the cosine of x with negative 12/13. All right, so then we just simplify this fraction. So we can do a little chop here. Whoops. And this is going to be 13/13 plus 12/13 is 25/13 all over 2, which I'm going to put over 1. And that is all under this positive square root. So now we can do keep, switch, flip. This is 25/13 times a half is the same as dividing by 2. So we get 25 over 26. So square root of 25, 26. The square root of 25 in the top is 5. The square root of 26 is just root 26. And then if we rationalize that by multiplying top and bottom by root 26, which this looks like a little bit of a mess, so I'm going to fix that for you guys. So we get 5 root 26 over 26. And again, that is positive. So that is our answer. All right, let's move on to number 12. And we've done a problem very similar to this a couple of times in class. We're going to rewrite this in terms of the first power of cosine. So first thing I need to do is write this as sine squared times sine squared. And then we can use that lowering power formula for cosine, which says 1 minus cosine of 2x over 2 times 1 minus cosine of 2x over 2. In the numerator, we're going to have to FOIL these. And if you do that correctly, 1 times 1 is 1. And then we'll have a minus 1 cosine of 2x and another minus 1 cosine of 2x. We actually have minus 2 cosine of 2x. And then plus cosine squared of 2x. And in the denominator, 2 times 2 gives us 4. All right, so we're going to have to use lowering powers again with this cosine squared of 2x. So that is going to get replaced with that formula. All right, so my next step, I'll have the 1 minus 2 cosine of 2x plus 1 plus cosine 4x, because if this is my x now, 2 times 2x gives me 4x. Oops. And then that's all going to be over 2, which is all going to be over 4. And now we just have to simplify this. Since everything has the first power of cosine, from here it's just simplifying. So first, 1 divided by 4 is a fourth. 2 cosine 2x divided by 4 is actually, a minus 1/2 cosine of 2x. And then right here, 1 divided by 2 divided by 4 gives you an eighth. Plus, this is 1 cosine divided by 2 divided by 4, so that's an eighth cosine of 4x. And then lastly, I'm just going to combine some like terms. 1/4 is the same as 2/8, so 2/8 plus 1/8 is 3/8 minus 1/2 cosine of 2x plus 1/8 cosine of 4x. And I'm just going to leave my answer like that. All of my like terms are combined. If you really wanted to, you could take out a 1/8 and make this, you could take out that GCF, but it does not make a difference. All right, number 13 through 18 are dealing with finding the exact value of some trig expressions. So in these, we have to think in terms of our unit circle and the restricted domain of those inverse trig functions. So in number 13 here, we have to think of our unit circle. Where on the unit circle does sine have a value of 1/2? Well, that happens at 2 places. It happens over here at pi/6, and it happens over here at 5 pi/6. But if you think of your restricted domain for sine inverse only can have values on this half from negative pi over 2 to positive pi over 2. So the only value that works here is this one. So this is going to equal pi over 6. All right, in our next one, we have to work from the inside out. So first we have to figure out what is cosine of 5 pi over 6. Well, that's just on your unit circle. So hopefully you can see that if you look at 5 pi over 6, the x value there is negative root 3 over 2. So basically what we're trying to find is the cosine inverse of negative root 3 over 2. So again, we're asking ourselves, where on the unit circle is the x value equal to negative root 3 over 2? Well, that happens at two places. It happens over here at 5 pi over 6, and it happens down here at 7 pi over 6. But again, cosine inverse has a restricted domain. So that restricted domain goes from negative pi to 0 pi. So this is where we can pick our points from. And notice that the only one that works is 5 pi over 6. So this actually does end up giving us simply 5 pi over 6. Okay, number 15 should be kind of sticking out as a red flag. Your sine value can never be outside of -1 to +1. So this you cannot do. So in this case, this is undefined. So you don't have to do any work with that one. Number 16, we have cosine inverse of 1. So we're going to start with that. So hopefully you realize that cosine has a value of 1 at 0 pi. So basically we're just finding the cosine of 0 pi. And that, I mean, you can draw a unit circle, but since it's just cosine, we know that cosine of 0 pi is right here at the point 1 comma 0, and that has an x coordinate of 1, so this does just end up being equal to 1. So that one's pretty straightforward. Okay, number 17. We're going to start with figuring out the tangent of 4 pi thirds. So 4 pi thirds is the value -1/2 comma negative root 3 over 2. So we're going to divide that y value by the x value. So the x value is negative root 3 over 2. And then if we divide by a -1/2, that's the same as multiplying by -2 over 1. So for this, we're going to end up with positive root 3 as that value in the parentheses there. So basically, we are just trying to find what is the tangent inverse of root 3. So we're thinking of our unit circle, and we're asking ourselves, where on the unit circle does tangent have a value of root 3? Well, we know it's at two places. It's definitely down here at 4 pi over 3, because that's what we just found out. But it also happens up here in quadrant 1 at pi over 3. So these are the two places where the tangent gives you a positive root 3. But remember, there's a restriction on that domain. So for tangent, you can't use these two values here because the y value of those two places, the x value of those two places is 0, and we cannot divide by 0. So remember, tangent is y over x. So that's going to give us some issues if we do that. So this part of the unit circle is the restricted domain of tangent inverse. And notice the only point that is going to work for our situation here is pi over 3. So the tangent inverse of root 3 is pi over 3. All right, and last but not least, let's find the sine inverse of sine of 3 pi over 4. So start with this. On your unit circle, 3 pi over 4 is the point negative root 2 over 2, comma root 2 over 2. So the y value is root 2 over 2. And now we can find the sine inverse of that value. So we're finding the sine inverse of root 2 over 2. All right, so if we get a unit circle out here, we're asking ourselves, where on the unit circle does sine have a value of root 2 over 2? So that happens in two places. It happens here at pi over 4 and here at 3 pi over 4. So for pi over 4 and 3 pi over 4, we have to figure out for the restricted domain of sine, which one of these is going to work. So sine inverse's restricted domain is from negative 2 pi to positive 2 pi. Or sorry, negative pi over 2 to positive pi over 2. So the only choice that's going to work here is this pi over 4. All right, so that's our answer for number 18. Okay, we are going to move on to number 19, which says find the exact value of sine cosine inverse of 3/8, and we're going to include a drawing. So first, this right here gives us some information. So if we know that the cosine inverse is 3/8, we're actually just going to draw any old right triangle. It doesn't really matter what it looks like. And I'm going to say that this is angle theta there. And I know if that's, like, this whole thing is my theta, my adjacent to theta has to be 3, and my hypotenuse has to be 8, because cosine is adjacent over hypotenuse. So I can use Pythagorean theorem now to figure out the opposite, or that other leg. So I'm going to say a squared plus 3 squared equals 8 squared. If I subtract 9 from both sides, 64 minus 9 is 55, so a squared is 55, which means a has to be root 55. All right, so now I know that the sine of theta is my opposite over my hypotenuse. Well, my opposite is that root 55, and my hypotenuse is 8. So root 55 over 8 is our answer. Okay, 20 is kind of along the same lines, but it's a little more complicated because now we just have tangent inverse of x right here. So it's not just going to be a number. So the first thing I'm going to do is put this x over 1. So I'm going to just, again, draw a generic right triangle here and say that this is theta. So theta is this given information inside the parentheses here. So my tangent is my opposite over my adjacent. So in this case, x over 1 is my opposite over my adjacent. And I'm going to have to use the Pythagorean theorem here. So 1 squared plus x squared is equal to the hypotenuse squared, or c squared. So if I square root both sides, I end up with the square root of 1 plus x squared equals c. So that is the length of my hypotenuse here. All right, so now I have to figure out what is the sine of theta. Well, in this case, the sine of theta is going to equal my opposite, which is x, over my hypotenuse, which is that 1 plus x squared. Okay, I'm going to move this stuff over so you guys can... Whoa, didn't want to rotate it. All right, I'm having some technical difficulties here. Give me just a second. All right, well, that's fabulous. Let me get back to where we were with that one. So we were just to this point where we were saying sine of theta is our opposite, which was x, over our hypotenuse, which was root 1 plus x squared. So if you need that, you'll just have to rewind a little bit to get back to that point. But we actually need to rationalize this. So I'm going to go ahead and multiply the numerator and denominator by 1 plus, or the square root of 1 plus x squared. So in the numerator, I'm going to end up with x square root of 1 plus x squared. And then in the denominator, when I multiply those together, I just end up with 1 plus x squared. So yes, that is kind of a complicated expression, but since we didn't know what x was, It just says to write it in terms of x, so that would be the expression for sine of tan inverse of x. All right, let's move on to number 21, and these are in section 7.5 where we were solving trigonometric equations. So first of all, in 21, we need to get cosine x by itself. So we're going to go ahead and add 3, and we get 6 cosine x equals 3, and then we'll divide by 6. So these here cancel, and we end up with cosine x is equal to 1/2. So here's the question you're asking yourself now. You're asking yourself, where on the unit circle does cosine give me a value of 1/2? And that's going to happen at 2 spots. It's going to happen up here in quadrant 1 at pi over 3. And it's going to happen down here in quadrant 4 at 5 pi over 3. Now, since it says find all solutions, and it doesn't give us an interval, what we have to do is say, first of all, x is pi over 3 plus, and then if we go around, we end up back at that same spot right here. And I could keep doing that forever and ever and ever. So I can just add a whole turn around the unit circle, which is 2k pi. So you could just keep going 2 pi around forever and ever. So that k just means you keep rotating around. The other solution is the same idea. So if I start here at 5 pi over 3, I can go around and get back to that same spot. So I can just keep adding 2k pi. So 5 pi thirds plus 2k pi is my other part of the solution. All right. 22 is going to involve a little bit of factoring. So I noticed that 2 cosine x and cosine x, there's a GCF of cosine x. So we're going to take that out, and then we're left with 2 cosine x plus 1. That still equals 0. So now that we have this factored, we can split this up into 2 parts. So we're going to set cosine x equal to 0 and solve that. And we're going to set 2 cosine x plus 1 equal to 0 and solve that. So cosine x equals 0 at 2 spots on our unit circle. So it happens up here at pi over 2. And it happens down here at 3 pi over 2. Okay, so notice that these are exactly 1/2 of a way around the unit circle. So instead of writing both of those plus 2k pi, we can just start with this point at pi over 2. So I'm going to say x equals pi over 2. And then I can just add k pi. Because if I add 1 pi, I'm going to get here. And if I add 1 more pi, I'm going to get here. 1 pi get here, 1 more pi get here, 1 pi get here, 1 pi get here, and so on and so forth. So I can just add any multiple of pi to get to the next point that has a cosine value of 0. All right, in this part over here, we're going to have to subtract 1. So we get 2 cosine x equals -1. And then if we divide by 2, we end up with cosine x is -1/2. So now again, I'm asking myself, where on the unit circle does cosine have a value of -1/2? Well, that happens at 2 pi over 3. And then it happens down in quadrant 3 at 4 pi over 3. All right. So these are not any special distance apart from each other, so we're just going to have to say for that part of the solution, x equals 2 pi over 3 plus 2k pi. You'd have to go all the way around to get back to this spot here. And 4 pi over 3 plus 2k pi. So those would be my other parts of the solution. All right, number 23 is our last solving problem. And this one is one where we have to factor. So this is of the form 2u squared minus 1u minus 1. So instead of saying sine x, I'm replacing the sine x's with u. And hopefully you see that could be factored as 2u plus 1 times 1u. So it's 2u plus 1 times u minus 1. And if you FOILed that out, 2u times u would give you u squared. And then the outsides are minus 2u plus 1u is negative 1u. And then positive 1 times negative 1 is negative 1. All right, so instead of putting 2u, I'm going to say 2 sine x plus 1 times sine x minus 1 equals 0. And then once you have that factored, you can just split this up into two parts. So we're going to say 2 sine x plus 1 equals 0 and solve that. And sine x minus 1 equals 0 and solve that. Now this one is just asking for the solutions on the interval, so we just have to find the solutions that are physically on the unit circle. So we don't have to think about adding k pi or 2k pi or anything here. So first I'm going to subtract 1 to get this solution on the left-hand side. So I end up with 2 sine x equals negative 1, and when we divide by 2, we end up with sine x is negative 1/2. So we're asking ourselves, where on the unit circle does sine give us a value of negative 1/2? Well, that happens down here at 7 pi over 6. And it happens down here in quadrant 4 at 11 pi over 6. Okay, for this part, we're going to add 1, and we get sine x equals 1. So where on the unit circle does sine have a value of 1? Well, that's only up here at pi over 2. So we've got 3 solutions that are physically on our unit circle or on this interval. So we're going to say x equals 7 pi over 6. 11 pi over 6 and pi over 2 are the 3 solutions for that equation. All right, now this last little part just has to do with the graphing of the inverse trig ratios. So in this first one, we're going to graph the sine inverse relation. And then we're going to highlight where it's actually a function. And for this one, we're going to graph the cosine inverse relation. And then we're going to highlight where it's actually a function. So it's that restricted domain. So what I do is I actually turn my paper sideways and pretend I'm graphing sine. So I'm actually physically turning my iPad sideways when I do this. And I'm saying that this is... Since this is positive, this is actually 2 pi, this is pi, this is 0, this is negative pi, and then this is negative 2 pi. And then on my x-axis, this is negative 1 here, and then this is positive 1 over here, and then in between we have a half. All right, so if I graph this, remember sine has a value of 0 at 0. Okay, and then at pi, it's back at 0. And then at pi halves, it has a value of positive 1. And then on this side, it goes like this. So at negative pi, it has a value of negative 1. And then it kind of just keeps repeating that pattern. So we've got these points here, so it's going to kind of wiggle through like this. You can see that wave-like motion. I kind of got a little off kilter here. I think I need to fix one of my points. Got a little bit of an issue with one of my points here. So this should actually be at pi halves. We're at -1, and I erased my -1. And then at negative pi, we're back up to 0, and then up to 1. And then at -2 pi, we have a value of 0 again. So I had one of my points in the wrong spot, and that kind of messed me up. So that whole thing is the sine inverse relation. So now I'm going to grab a highlighter, or you can like bold this part. And I know that this is definitely not a function because it does not pass the vertical line test. I can only go through one point on the vertical line, and I'm going through many, many points. So that's why we restrict the domain just from -pi/2 to +pi/2. So this highlighted part in the middle here, this just from -pi/2 to +pi/2 is the sine inverse function because it has that restricted domain. Okay, for cosine inverse, we're again going to go from -1 to +1. This is going to be pi, this is 2 pi, this is -pi, and this is -2 pi. And then that one at 0 has a value of +1, and then it kind of is symmetric about that x-axis. So I'm just kind of drawing these points in so I get that symmetry or that cup shape. So in this case, we're going to have it kind of just be periodic through here. It's kind of hard to draw sideways, but that's all right. So that is definitely not a function because, again, notice if I draw a vertical line, I'm hitting many, many points, and we can only have it hit through one point. So what I do is when we restrict our domain from 0 to pi, so that we only have one point, and that would pass that vertical line test. So from 0 to pi is my cosine inverse function. And again, that has that restricted domain. So that's why in those previous problems, we had to look at the unit circle and see like where the cosine inverse actually works. So for sine inverse functions, from -pi/2 to +pi/2 is this part of the unit circle. And then for cosine inverse functions, 0 to 1 pi is this half of the unit circle. So that's why we look at those portions when we're figuring out those sine inverse and cosine inverse problems. All right, and then lastly, we're going to do the inverse tangent relation and then highlight the inverse tangent function. So this is going to be the tangent inverse relation to start. So I'm going to label my axes. This is -1, -2, -3. This is 1, 2, 3. And then I'm going to say this is pi/2. This is pi. This is -pi/2. And this is -pi. All right, and we know for a tangent, there are asymptotes at pi/2 and at -pi/2. And then tangent has a point of 0 at 0. And then at pi/4, it has a value of 1. At -pi/4, it's at -1. And remember, tangent inverse has the asymptotes, so it kind of just like gets closer and closer to those dashed lines. And then it kind of repeats that same pattern. So it'll have a point here, a point here, a point here, and then it'll kind of snake through like so. And then down here, same pattern, a point here, a point here, a point here. And it kind of snakes through that this way. All right, but again, this is not going to pass the vertical line test, so we restrict the domain and make just from negative pi over 2 to positive pi over 2 our function. So this portion here is actually our inverse tangent function, and it's with that restricted domain. So again, if we bring that back to the unit circle, the reason we have holes here at pi over 2 and at negative pi over 2 is because we have asymptotes there. We can't divide by the x value because the x value at those 2 points is 0, and we only consider this portion of the unit circle so that it actually is a function. All right, I hope that helped. If you guys have any questions, I would recommend emailing me, and I will get back to you as soon as I can. All right, thanks, and we'll see you guys soon.